Nathanael Scharli.
Maybe you should. Oh, yeah, in case someone is.
Okay, does this work? Okay, good. Today's speaker is Nathanael Scharli from the University of Bern, from the software composition group under Professor Nierstrass. His talk is about traits, and actually this is interesting because I thought already 5 or 6 years ago there was nothing new to invent in the area of inheritance, but it turns out I was wrong. Nathanael not only developed traits, he also just had his defense of his PhD, I believe in January, is that right?
February.
February. So he successfully defended his PhD and showed that there's actually a number of interesting things that can still be done in this area. And with that, I'll hand it over to Nathanael.
Okay, thank you very much. And thank you very much for attending my presentation. As Andreas already said, it's about traits, which is a composition mechanism for object-oriented programming languages. I will start my presentation with the motivation from my work. I will talk about problems with existing approaches and from there derive goals for a new and hopefully better composition mechanism. Then I will present our solution, which is called traits. I will show how this solution addresses the problems we have identified, and I will also see, how does it meet the goals, and yeah. I will then, in order to show the practical usefulness of traits, I will talk about a case study that we did where we used traits to refactor the Smalltalk collection classes. Then I will briefly talk about the implementation of traits in Squeak, and I will end with the conclusions. As a motivating example, suppose that we want to build a library of graphical objects like circles, rectangles, and polygons, and that besides the very basic black and white versions, we also want to have more sophisticated versions, like versions with color or a border around it or such, things like that. Now, the basic idea is that it would be really nice if we could build all these different graphical objects from a small set of building blocks that correspond to all the different properties that we use in this library. This means that we would have building blocks corresponding to geometric properties like circle, rectangle, or polygon, but also building blocks corresponding to other properties like colored or bordered. Using this design, we could then build our basic black and white circle using the simple building block circle, and similarly, we could build rectangle and polygon. But what is much more important is that we should be able to build up more complex objects, such as colored rectangles using 2 building blocks, kind of combining them, rectangle and color, or to build up a circle with a color and a border from 3 building blocks. Now, let's see how we would implement this in one of the recent object-oriented programming languages. Now, most of these languages, the recent ones like Java or C#, are based on single inheritance. So we would probably create an inheritance hierarchy. We would probably have an abstract root class. I call this visual, and then have concrete classes for all the different graphical objects like circle or rectangle. We would also have a class, maybe bordered circle, which inherits from circle in order to make sure that we can actually reuse the facilities that we already implemented in circle, and then we would just add the behavior or the facilities for a border in this class. Similarly, we would have bordered rectangle as a subclass of rectangle to make sure that we can use the rectangle facility. But now we already run into the first problem, because what we would really like to do is to actually also now reuse the border code in bordered circle also for bordered rectangle. But with single inheritance, this is not really so easy, because with single inheritance code reuse means, yes? Right, yeah, I mean, I could address that, but I'll just go a little further. You will see probably more realistic examples. So anyway, with single inheritance, this means that you should put that code into a common superclass, and here the only common superclass is visual. But this is not really an appropriate place for that bordered code, because there are many subclasses of visual, like circle or rectangle, that are not bordered and therefore should not inherit this code. And so as a resort, oftentimes the features are just duplicated in both of these classes. And this is not only unsatisfying, it's also one of the problems is it's very different from what we had imagined, because what we had imagined is that we could actually use that code and refactor it, factor it out in a place where it's independent of the whole inheritance hierarchy, and then we should be able to use that feature across the inheritance hierarchy for all the classes that actually need to be bordered. Now, of course, this is just to also come back to that question, it's really just a little illustration of code, of course, depending on how you would actually, for what you would use it. Maybe that's not the right approach to do it anyway, but I will have more convincing examples later. So it's just kind of to start up and show a little bit of the problem. Right, yeah. Anyway, so as we have seen, single inheritance is clearly not expressive enough to solve certain problems, but we are not really the first to discover this. In fact, language designers have already proposed several alternatives for precisely these reasons, alternative forms of inheritance with several notions of multiple inheritance and also Mixin inheritance being the most popular ones. However, both of these approaches also suffer from other problems, and I will now illustrate a few of them. The idea of multiple inheritance is that a class can not only inherit from one class, but just from multiple classes, as the name suggests. So in our example, this is useful because it means that we could actually factor out the bordered behavior into a separate class and then make bordered circle inherit both from circle and from border. Similarly, we could make bordered rectangle inherit both from border and rectangle, and so we would actually be able to share the bordered code among both these classes. Now, what looks so easy and simple at first is actually can get quite hairy and problematic when it comes to the details. As an illustration, suppose that we want to create a new version of a circle that contains features a synchronized drawing method so that we can actually use it in a multi-threaded program. Now, in the first attempt, we might do this by creating a subclass of circle and then override draw so that it first acquires a lock, then calls the super method, then releases the lock, and finally returns the result. Now, of course, since we have so many different objects in our framework, we would like to reuse that code so that we can actually also use it to synchronize rectangles or other objects. Now, with multiple inheritance, reusing code means putting the code to be reused in a common superclass. So what we would do is to put that into a new class, synchronized drawing, and then make all the subclasses inherit from it. Unfortunately, this does not quite work because the reference to the super method here is in pretty much, in most multiple inheritance models, like the ones of C++, statically bound. So it always refers to a superclass of this class synchronized drawing. However, it should refer either to circle or to rectangle, else that doesn't work. So what we need to do is we need to replace that call with a call to an abstract method that then serves as a hook, which needs to be overridden in both subclasses. This means that in each of these subclasses, we now need to implement two methods. On one hand, we need to implement the method direct draw so that it actually returns the draw method of the superclass. And then we also need to implement the draw method to clarify that we really want the draw method from synchronized drawing, because we have here we inherit two different draw methods, and so it would be a conflict. And we need to say, we really now want synchronized circle to use the draw method from synchronized drawing. And the exact same thing we also have to do on the side of synchronized rectangle. Now, as you have seen, the whole solution, even though the original problem was very simple, is actually quite complicated and at first a little hard to understand. It also still involves duplication of two methods in both subclasses. And it involves explicit class references, at least in the C++-based version, to actually resolve the conflicts, which makes the whole system a little fragile. Yes?
It seems easy in your scenario because you just make sync draw and the subclass of visual contains draw. And there's no problem, right?
I mean, it depends on what language exactly you're using. In C++, there would still be a problem.
If we would be using beta, you were right.
I mean, it's clear,
Is there any problem in C++ that prevents that from working?
Sorry?
You'd wind up in a loop because it's draw.
Right, yeah.
The implementation of draw, calling draw, you wouldn't get down to the circle.
Okay.
Right. I mean, of course, I'm talking here about multiple inheritance. There are like lots of different flavors of it, and I just kind of use now the C++, but you run into kind of such problems, generally. So then Mixin inheritance is another approach that was designed to avoid multiple inheritance problems, and the idea is that a class can still inherit only from a single superclass, but when a new class is derived from a superclass, some reusable behavior can kind of be mixed in. So in our example, this means that we could put the bordered behavior into a mixin, and then bordered circle would still only inherit from circle, but we would say that when we perform this inheritance, we kind of mix in the delta m bordered, this mixin, into it, and so we would actually obtain the mixin, the behavior or the facilities provided by m bordered, we would obtain in the subclass. Similarly, we could then do the same thing for rectangle. So when we derive bordered rectangle from rectangle, we just mix in the mixin m bordered. And again, this allows us to actually reuse the bordered code. Now, unfortunately, also mixin inheritance is quite problematic, especially when multiple mixins are composed. As an illustration, suppose that we want to use two mixins, m bordered and m colored, and apply it to the class circle in order to derive a new class bordered colored circle. Now, because mixin inheritance is based on single inheritance, the mixins have to be applied one after the other. In our example, you can say, first we apply the mixin m bordered, and then we apply the mixin m colored. Note that in this illustration, I also show the intermediate classes. These are kind of anonymous classes that conceptually often get created whenever a mixin is applied. Now, a very interesting method here is the method astring, because it's provided by all three entities. Now, unlike with multiple inheritance, with mixin inheritance, this conflict is now implicitly resolved, because the mixin provided by the method provided by the last mixin, in this case this is m colored, implicitly takes precedence, and that's what we obtain in bordered colored circle. Yes?
The classic mixin system, the flavor system has method combinators to get around this.
Right. So,
the whole design is you get to specify things wrapping one another.
Right. So with this with some versions, for example, the flavor stat, but that's possible. But again, I cannot go into all the details there. But what made it really through now in kind of more mainstream languages, like there are several implementations of mixins in Java or also in Smalltalk, and there, if you don't have this this flexibility of flavors with all these adaptations of methods, which usually are not available in our object-oriented languages, we don't have that, and so it's kind of a trade-off. It adds a lot of complexity if you would have to use that. So yeah. Right. So it's a little unfortunate, but most recent versions don't really offer that. Now, the problem is that this is usually not what we want, because we would much rather like to have a combination of the different astring methods in our bordered colored circle. But it's even worse, because from within this composite entity bordered colored circle, we cannot really do this, because the only thing we can do here is we can use super to reach up to the last implementation of astring that is available. But there are no linguistic constructs to actually reach up to the other. There is usually no such thing as super or whatever. So we cannot actually access these other implementations of astring, and so we cannot really recompose it. So even if we notice that we don't get the right thing, we cannot really recompose it right. And the only place where we can usually access all these different versions of astring is within the mixins themselves. But this means that the user has to kind of, change the mixins and put the glue code that says how this stuff is actually glued together into the mixins, which is, of course, not really right, because the mixins then get very specialized and are not so reusable anymore. So as a summary, we can say that problems with mixins that are conflicts are implicitly resolved, which leads to fragility with respect to changes. Then the composite entity is not in full control of the composition. So it's kind of results in a dispersal of glue code, so that the glue code is kind of dispersed over a whole inheritance hierarchy. And it's very hard then to see, okay, what's the reusable code, and what's the glue code, and what's really the final behavior of the composite. So being aware of all these problems, we can now state the goals for a new and hopefully in at least certain ways better composition mechanism. And clearly the first and foremost goal is we want to improve code reuse. But we would like to do this in a way that maintains understandability of the code. So intuitively, this means we would like to have an approach that if we have maximum code reuse, or at least really good code reuse, it should be as easy to understand, or maybe even easier to understand, as if we use kind of a trivial, approach based on code duplication or whatever. Then we would like to have relatively high robustness with respect to changes, so that our system is stable. And we would like to avoid dispersal of glue code, so that we can easily understand our system, and we can specify at one point how the different things should be glued together. Information hiding is not on that list, because for us this is kind of a separate issue. It's a very important issue. Well, I mean,
I don't want you to redefine the data string code or reach into my guts, right? It's going to make that harder.
Right, of course, it's true in certain ways, but let's say now if you have 3 components that all make A-string public, you can actually call it, and then you say, okay, my new component should use all these 3 components, then the new component should have the power to say how the different A-string methods should be composed. Of course, you cannot.
The Mixin should be able to remove that power.
Right, of course. But if someone removes that power from you, then of course you can't really, then it's kind of, it's bad luck in a way. But it's not really then up to the composition mechanism to figure out. I just would say, if you have the means to access something, you should be able to specify it in the composing entity. Yeah. Okay, so the solution we propose for this is to use entities called traits. And intuitively, that's now on a very intuitive level, traits really just kind of correspond to these building blocks that we saw in the very first slides, which means in particular that multiple traits can be composed to build up more complex kind of classes. A little bit more technically, traits are parameterized behaviors. They provide a set of methods, and they may require a set of methods that parameterize the provided behavior. So here we have a trait T-circle that provides area, bound, circumference, diameter, hash, and this provided behavior is parameterized by kind of getters and setters for radius and center. Now what's important that our traits, at least our basic version of traits, does not allow to specify any state. So they're really purely behavioral. Also note that from now on I will mostly use Smalltalk syntax in the examples because our primary implementation of traits is in Smalltalk.
State include blocks or not?
No, I mean, no.
I'm saying that the synchronized draw example doesn't work with traits then.
No, you can. It just means you cannot specify. You can make a requirement for. You can make requirement for a lock that just kind of needs to be provided when you use the trait. You say, okay, my locking.
You had require lock and release lock as methods. That's why I'm asking. No, that was part of the synchronized draw.
Yeah, so you can require them on the right without saying where the state is on.
No, but his trait introduced those methods. That's why I was asking.
No, I mean, so I don't think there's a problem. If you have a trait that, let's say, the trait synchronized, we'll come back to this example. You can have require lock, and the method require lock can use an accessor lock that then is a requirement of that trait. And when you use it, you have to say, okay, lock returns something from a database, or it returns something, a slot, an instance variable.
The real issue here is that you want to avoid well-defined behavioral aspects that you need to redefine later when you compose the whole thing. That's why there's no
There seems to be an implication that somehow the root object has to define as many locks as you're ever going to need in any number of mixins in advance. Right? The flexibility is not so good here.
Yeah, I guess you're right. Yes.
It has to come from somewhere.
Yeah.
Right. But I still think, I mean, generally, it's not really a restriction because, yeah, I'll show you how afterwards they're composed, but it's not really a restriction because you can always make a requirement for the state that you would otherwise define, because the traits are, as I will show later, are not going to be objects that stand alone. So they're all going to be parts of classes anyway. And so, yeah, I will come to that, yes?
Are you going to motivate why you're making it an actual restriction that there's no state constraint?
Right, I can talk about that. So the reason is, when we were looking at, there are more powerful versions of inheritance, and for some reason, they never really made it very much into mainstream. So even most recent languages, oftentimes they kind of say, we just use interfaces and single inheritance. It just gets too hairy. And so what we said is we would like to have an approach that gives you allows you to solve a lot of problems that you cannot solve with single inheritance, but it shouldn't be too complex. We wanted to make the simplest approach first that really works, that allows you to do a lot more, and state oftentimes is not really a problem, but it's not really a problem if you cannot define it. In fact, even the traits get more general. You don't really say earlier, but at the same time, you avoid a lot of problems like initialization, and also, if you have a diamond situation, for example, should the state be multiply inherited or singly inherited? So state makes it a lot more complex, but I don't think you lose super much if you don't have them. So that's why we said in the first attempt, we just do not allow it, but
There are a lot of useful traits that have state, like listeners or the next field or...
I agree, but the thing is you can still do it. In fact, when you then just use the trait, when you use the trait in a class, then you just have to define, and that right now in our implementation, that goes even automatically. You just have to define a slot or a field for that, and then it just is a little bit of a, you can still implement all these examples, because what you really want to share is the implementation. Defining a slot can be done automatically. What you want to share is the implementation. And if you,
Practically speaking, all of the bad examples of multiple inheritance I've seen basically all came from using state. I have seen wonderful examples of multiple inheritance where multiple inheritance has been used just right, and I was amazed that after doing 5 years of C++, I could actually learn how that was supposed to be working. So I personally, I think this is one of the major advantages actually here to say, okay, there's not going to be state, because we know that for many users, state is really critical to handle. And not having it in there means you're designing your system in a way from day one to not assume any state in these behavioral building blocks. Which means later on you can actually redefine whatever is needed, because you're not only on assuming that there must be state there which does X or Y.
Right, and you can also look at it from this point of view in like Java or C#, you have interfaces which are just specification. Of course, they're used mainly for types, but it's kind of a multiple inheritance of interfaces. Now, we say, okay, you can share behavior, which gives you a lot of power, but we don't quite say you can reuse state. Also, an example for where state is sometimes too early put into traits, if you could put it, let's say we make a trait rectangle. You probably say, okay, my trait rectangle has origin and corner. So you would say this is state, these are two slots. Then let's say you want to use, in our system, Squeak, we wanted to use, add rectangle to a class rectangle morph. Now rectangle morph is a visual object that already knows its extent. It already has slots for that. If you then have the state in the trait, you kind of have too much state. Now, of course, you can always synchronize it, but it's not really right. Then if you can't do that, you're not even tempted, and you just say, okay, I need that behavior, and I then decide how to wire it together with the necessary state that may already be there, because multiple traits sometimes can share state.
Does the state have to come from the object that you're relating the trait to, or can it come from a third object that's either mixed in or otherwise?
It comes from the class, where you mix in the trait. So, but I will show that here. So. How do we use traits? So if we build classes with traits, let's say we want to build the class colored circle, what we do is pretty much the first step is as usual. We say, okay, what should be the superclass of this class? In this case, this should be the class visual. Then we define the state. So here we say we need to have 3 slots, RGB, radius, and center. Then we define or we specify what traits this class should use to incorporate the necessary behavior. And finally, we implement some glue methods that connect the traits together and that also access the necessary state. So this is really how traits are kind of designed to be used. What we see is that traits are really the behavioral building blocks of these classes. So everything else still is in the class. The glue code and also the superclass is still there, and the slots. But the behavior of the colored circle really comes in as traits instead of putting in individual methods. And then we also see that traits do not really replace single inheritance. Instead, they are an extension of single inheritance, and traits just provide better modularity within a class. Okay, so one of the advantages of traits is that the composition rules for composing traits are actually quite simple. In fact, there are only 3 rules. The first rule says that class methods take precedence over trait methods.
Right, so there goes the information hiding.
Right. Of course, you can say if we have a model where you say if a trait says certain methods cannot be overridden, then the class cannot override it. So of course you can only do, so there are independent issues. It doesn't mean that it's always possible, but it's the same thing as with inheritance. If you want to inherit from a subclass, from a class where everything is private, you can't do anything. But it doesn't mean that inheritance is bad, it just means that maybe it was too strictly encapsulated. Okay, so as an illustration of this, suppose again we want to build our class colored circle, and we use 2 traits, t-circle and t-color. Now first we see that we have here open requirements, radius, center, and RGB. And so what we need to do in order to make this composition complete, we need to say what is radius, center, and RGB in our example. So we need to implement glue methods, and in this case they will probably be just accessors for the state. Now the class is complete, but it doesn't necessarily mean that it already has the right behavior. For example, the method hash provided by t-circle only takes radius and center into account. Now we may say, we are here talking about the colored circle, so we really would also like to take the RGB value into account when we compute the hash. And so we would like to specialize that behavior. And how we can do this is that we now say, this is exactly where the first rule comes into play. If we implement a method hash on the level of the class, then this hash method overrides the hash methods that we obtain from t-circle, and so we can actually specialize behavior that we get from traits. Now, the second rule says that trait composition is commutative. So as a consequence of this, conflict resolution is always explicit. So what does that mean? Suppose that both t-circle and t-color provide a method hash, then according to our composition semantics, this leads to a conflict that has to be explicitly resolved. And this can be done in 2 different ways. One way is to override the conflict with a glue method, because according to the previous rules, glue methods on the level of the class take precedence over the methods from the traits. So if we implement the method hash in the class colored circle, this method takes precedence and kind of therefore disables the conflict because both of these methods are now disabled. Now, oftentimes it's useful to be able to access the method hash, the 2 different versions, the conflicting versions from within this new implementation. And we can do this using a construct that we call an alias. This means that we can give each of these methods an alias name in the composition, and then we can just use this name to actually access the behavior that was there. So we can say the method hash in t-circle should be available under the new name circle hash, and so we can use it as a regular method. So we can just send a message. Now, another way to resolve conflicts is to exclude one of the conflicting methods. This is useful if, for example, we say, the method hash in t-circle is exactly what we want. So we do not want the method hash in t-color. So when we compose this, we say we want to use t-color, but we do not want to use the method hash of t-color. So we exclude it, and the conflict goes away. The last, sorry? The alias on the required methods, no. Right now, you can't do that.
Okay, so the problem is they both might want to use a state variable f, and it needs to be a different state.
Right, exactly. And this is also, the traits is kind of one step of a model that is that we are developing, and we are actually dealing with that issue on the level of the encapsulation model. So we can then say, so it's not really dealt with on the level of this composition mechanism here. But we have a way of dealing with it, but yeah, it's kind of a separate issue. At least I think it's an issue that is very adequate to be, to ask how that really works, because it also belongs in here, but we just dealt with it in another part. Then another composition rule, which we call the flattening property, says that traits methods have no special semantics. So what does it mean? If we have a class circle that inherits from visual and uses a trait t-circle, and here t-circle has a method area that has a certain implementation, self radius squared, then the question is, what does this actually mean? And the answer is that the meaning of this is exactly the same as if this method were implemented in the class. So this means in particular that self-radius refers to the method radius in the class. The same thing also applies for diameter. It has the same meaning as if it were implemented in the class. A little bit more interesting is the method hash, because the method hash has a supersend. But again, the flattening property holds. That means traits methods have no special semantics. They have the same semantics as if this method were implemented in the class. And so super actually refers to the superclass of the class where the trait is used. So in this case, this is the class visual. And so this code, super hash, would actually refer to the hash method implemented in visual. Now, the flattening property is especially important because in the same way as classes can be composed from traits, also traits can be composed from other traits. So we have here a trait T-circle that is composed from another trait T-circle math. And the rules for this composition are now exactly the same as if T-circle would be a class. This means that we can add new methods on the level of this trait T-circle, and we can also override certain methods if we are not happy with them. Now, if we use this composite entity in a class, then the semantics of the whole composite is, again, determined by the flattening property. This means that the non-overridden methods of T-circle mass have the same meaning as if they were implemented in T-circle, and requirements that are not satisfied are equivalent to requirements on the level of the next entity. And by flattening again, we end up with a structure that has a well-known semantics, and this is exactly the semantics of the whole composite. Now, besides the fact that this makes it easy to understand and reason about structures built with traits, it's also nice because it allows to look at structures built with traits in multiple ways. On one hand, we have a flat view. This is this view where it looks like everything were implemented in one class, and we can understand, because of the flattening property, everything by just looking at it as if it were implemented in the class circle. So it doesn't matter from where these methods come from. But we also have multiple composite views that show us how the circle class is really built up from smaller entities. And what's particularly nice about these composite views is that the reusable methods, so the methods that we use from traits, are separated from the glue methods that kind of say, how do these methods collaborate together? And so if we already know the reusable traits, because we have used them in many other places, we only have to look at the glue methods to really understand the whole composite structure. Okay, now, since we now know how traits are composed, let's go back to our problems and see how we would solve them with traits. So first, the problem where we want to share some synchronization code or whatever else of adaptation code between multiple classes. Now with traits, we just put that code into a trait. So we call that trait here T-synchronized drawing. And then we can use that trait in all the classes that actually need to be synchronized. Now, of course, here, this is not shown in the example. This trait T-synchronized drawing, you can see on the right side, I just didn't show that for space reasons. There would be requirements. There would be requirements for a semaphore or like a monitor or what.
Yes.
Right.
You're not actually implementing acquire lock and synchronized drawing.
No, you can implement acquire lock and release lock. You can implement everything except the access to the actual lock field. Yeah, but okay, maybe it depends on how you want to implement synchronized drawing. Sometimes you want to implement some wrapper code. Maybe you want to have some particular, some other kind of wrapper code, and you want everything except the actual reference to the instance variable you can actually implement here, and so that whole behavior you can reuse. So in this case, you're right. Acquire lock and release lock might be just, a call to a lock.
They exist so you can override them.
Right, but so it's not, in this sense, not the best example. But what is the point is that the whole behavior of this.
You alias something and then override it in the class. So
Right. Yeah. And so what's the whole point is, you can put all the behavior except the definition of the state into that trait. And so instead of using the state directly, you just always have an accessor method that does nothing else than returning the state.
But if you did override it, that wouldn't get rid of the requirement, would it?
Right, yeah.
The point is, suppose you want to switch to a different lock.
Yeah, suppose there's a requirement in T-sync drawing for semaphore, okay? And you don't have a semaphore in sync circle. So you're going to do a special implementation of a require lock that does it on a,
Actually, it might look
read
the
by
drawing.
write code, okay, to assembly code or something like that. And so you want to do a special definition of require lock, release lock. Well, great, but you still have to provide the semaphore because T-sync drawing requires you to give a semaphore, right?
Right, right. So what's the point is, let's say we have a very fancy way of acquire lock. Whenever we acquire lock, we want to do some other things. We want to, log it in the file or whatever else. Then all this code we can put in here. And so the only thing we don't put in is, instead of using acquire lock, we just say, we call an accessor method. And synchronized circle then has to say, okay, what is this, let's say, lock method? What is this? Maybe that's something that is not even an instance variable of synchronized circle, but it just has to be in this code. When synchronized circle uses that trait, it has to specify what it is.
Maybe you haven't gotten this yet, but did you have a story on how things like private would work for a private field in a trait?
Right. So I mean, this is again, this other part of it. And now in let's say Smalltalk, you do not have any access control. So this means even if you have single inheritance, when you have a class and you make a subclass of it, every feature of the superclass is completely, But so because our goal was to get to a better language. And so this is a composition. This was one part of it. This is a composition mechanism. The other part is an encapsulation mechanism. And we have these as two separate things because our language that we wanted to make sure that you can add it to every language, whether it has already an encapsulation model or not, and what kind of encapsulation model. So we separated these two issues. So this is really not just part of this. But I can afterwards, talk a little bit about the other.
It seems like it's far from obvious how that would work.
Yeah, I agree, but I think it actually does work. So, but yeah, it's not really part of this presentation, but I can talk about it later. Okay, now because of the flattening property, the supercalls here actually really refer to the draw methods in each of the respective superclasses. This is different from, like, let's say, multiple inheritance in C++, where the supercalls are statically bound. So here, because we have the flattening property, the behavior of this code, of this kind of composite, is now guaranteed to be the same as if the synchronization code were implemented directly in the subclass. So we can be sure that we are fine. Now, the other example is where we want to build a circle with border and color. We just have traits t-bordered and t-color. And now we create a subclass, bordered color circle, that just inherits from circle and then uses these two traits. Now, because of our semantics, this immediately leads first to a conflict, because string is provided by two traits. But unlike with mixins, we have now the full linguistic means to resolve this conflict within bordered colored circle. Because we can use super to refer to the string method in circle, and we can use aliases to refer to the string methods in t-bordered and t-colored. And so we can now implement an string method, for example, that concatenates all the different versions of string that are available. And we can do this, of course, provided that these string methods are really callable within the class bordered colored circle. So as an evaluation, we said that we would like to improve code reuse. And this is done by saying that classes can now be composed from traits. And traits can be shared across the hierarchy. So we actually really have more powerful ways of building up of reusing code. Then we said we wanted to maintain the understandability of the code. And we argue that in a certain sense, we even improved understandability of the code because of the flattening property that allows us to look at the code in different views. We can still look at it in a flat view, even if something is built from many different traits. We can edit and work with the code in a flat view as if everything were implemented in the class. But we also have composite views that allow us to look at the code in a more structured way.
I'm not buying this for the same reason as the yo-yo problem with Smalltalk. Sure, you can flatten it, but if you try and understand all the ways a particular class could be used in its subclasses when they haven't been written yet, this is what the information hiding is needed for, right?
Right.
It's very hard to reason when someone can override all of your methods in arbitrary ways.
Right, but I mean, here we are not, the trait thing really is, it's not about whether, it's implemented in Smalltalk so you don't have information hiding. What's the point is, let's say you have a class circle, or like you have a class, and you build it up from 20, 20 smaller components. Then sometimes it's useful to be able to say, I do not want to look at these 20 components because maybe all are foreign to me in order to understand the result. So in this sense, it's nice to have a flattened view where I say, okay, how would that look if it were implemented all in one class? But then sometimes you use.
How do you understand the meaning of order in isolation? I can't, right?
No, but you never will. But that's not the
But
point.
that was what I would like you to mix in, right?
What?
The fact that it's a bordered circle is supposed to mean something. It's not just whatever you decide to implement and call it a bordered circle.
So?
No.
When you do things like let you have blue code for these sorts of things, I take a circle and make it bordered in color. I have no idea whether the border is colored or not. You made an arbitrary choice in the display. But
No, but what's the point is, you have a composition mechanism, and like let's say mixins. There are many implementations of mixins. There is mixins implemented in Smalltalk, and if the mixins implementation in Smalltalk, there is no encapsulation. Then there is Mixin implemented in Java, and there you have public, private, they kind of use the same scheme. And you have Mixin implementation in other languages that have other encapsulation scheme. I think it's important that at least we believe that.
you can limit yourself to the underlying language's information restrictions.
No, actually, I think the goal was to have a composition mechanism that is separated basically from how you actually use encapsulation.
Flexibility does not imply better understandability. I agree that you're more flexible. That does not imply you're more understandable.
No, but our argument is.
But practically speaking, I think you are. I mean, I have looked at a number of large enough class hierarchy which use single inheritance to say, okay, any structure would help me to understand this better. I'm dead serious.
Right.
I can show you a few really bad examples for that.
Right. No, and also what our goal is, I come to the case studies that we performed. What's really the goal is we took Smalltalk code, and you have a class that, let's say, on one hand consists of 200 methods. And then we restructured it so that it uses 10 traits, where you have these methods. Now, in some cases, especially if you know these traits, it may be easier when you look at the class to say, oh, this class consists of these traits. I already have used these traits in 10 other places. I know what they do. Then I only have to look at the 3 glue methods that glue that together to understand it. But what's the point is, you have on one hand this, but you still can flatten it because of the flattening semantics. You also can look at it still with the 200 methods. And if you have what you had before and you have something new, then you can't lose anything. And so that's why we said, in a way, the understandability is at least as good. Yeah, okay. So anyway, the other goal was robustness with respect to changes. And our solution is fairly robust because of the requirement for explicit conflict resolution. Then the dispersal of glue code that we saw that was kind of required in other approaches like mixins, we do not have because the composite entity has, because of the linguistic design of the composition mechanism, full control of how something should be glued together.
But since it's changed, we don't actually have, because if I change one of the traits and it happens to have a name conflict, they break the other code.
Right, so of course, things can always be broken. So.
Languages like Java try very hard not to have this happen. That's why you have overriding fields and things like that.
But again,
if you add a field in a superclass, you don't break the subclasses.
Right, but traits do not have it. So what happens if you have a public method in Java, you add it, and 2 public methods in Java conflict, and if you add one, things can break.
100% successful. It's just they're better than just the default, which is that it always breaks.
No, but here it's.
So what happens in Java if you have 2 interfaces that
You
have a name
superclass, and it already exists in the subclass. In the subclass, you get the subclass field. In the superclass, you get the superclass field, and it just works.
Right, but.
No, I'm not talking about state. I'm talking about methods. Let's say I have 2 interfaces. Well, that's what we're breaks by default in Java 2.
Right.
Good point.
Yeah, it's really the same. Okay, now so far.
Private methods too.
Pardon me?
This breaks for private
No,
methods,
but
though.
the thing is here we didn't address the whole private issue. The whole private issue is separated, and we have a composition model that is encapsulation model that works with traits.
But you create extra methods that weren't otherwise there for glue purposes. So you're more vulnerable than the original Smalltalk was on this issue, right?
No.
No, the glue code is really implementing the requirements, and in some ways these are already there in the traits because the traits actually relies on them. So you could not possibly use that without having these methods. That's basically what the glue code is. The glue code is not extra methods.
I'm sure it is because you have as colored as string or whatever. You added new methods, right? Just so you could refer to them. Those methods are now in the namespace, including it.
Oh, you're talking about these things.
Yeah.
You are right. If you would choose the aliases so that they could come
underscore convention, it maybe makes it not so bad, but
well, this is an interesting point. Yeah. That's
But
Details you could hide those inside no spaces anyway.
Yeah.
right.
And I think you should.
Yeah, but generally, I mean, what Andrea said is really the case. Like in Java, if you want to have if you have two interfaces that have have a certain method that they require that happen to have the same name but should do different things, you can't really do anything. And that's why we do not deal with that here, but in our encapsulation model. Okay, so anyway, so far we have seen that traits have quite nice theoretical properties and they work with, as you said, toy examples. Now the question is, is this of any use in practice? And so that's why I'm going to talk briefly about the case study we performed where we applied traits to the Smalltalk collection classes. The idea of the Smalltalk collection class is to provide the programmer with a uniform way of accessing different collections. This means no matter whether we are dealing with a linked list or a tree, it should be possible to use the same kind of protocols to talk to such objects. So we should be able to have testing methods like isEmpty, includes, and enumeration methods like do and select, copying methods, whatever else. Now, looking at the collection classes in a little bit more detail, we can see that there are many different ways how these classes can be classified. So there are many different classification criteria. One of them is, for example, order. So there are unordered collections like set. There are explicitly ordered ones like linked list, or implicitly ordered ones like heap. Then there is extensibility is a criteria. We have extensible ones like array, or fixed size ones like array, or extensible ones like order collection. We have mutable and immutable collections, for example, string and other collections. And then we can also classify collections depending on how they compare their elements, whether they use identity or whether they use equals. So there are many different classification criteria. And now if we implement the collection hierarchy in a single inheritance language like Smalltalk, the problem is that single inheritance is just not really expressive enough to correctly model classes that can be classified according to so many different criteria. So as an illustration, if we start up with an abstract root class collection, and we say, okay, we have now a subclass for explicitly sequenced collection and one for implicitly sequenced collection. Then among the explicitly sequenced collection, we have fixed size and variable size collection, like array and order collection. But the exact same distinction also arises on the side of implicitly sequenced collection, because we have interval, which is fixed size, and variable sized collections with, for example, heap. Now, again, how can we share this code? And it gets even worse, because here we are only looking at two different criteria, but in fact, there are many more. So as a consequence of this, the Smalltalk collection hierarchy, even if it's considered one of a very nice piece of object-oriented design, it suffers from many problems. There is code duplication. There are methods that are implemented too high in the hierarchy. There is inappropriate inheritance, and there are incomplete protocols. An example of methods that are implemented too high is shown on this slide. Here we have the classes set and heap, which are both extensible, and they happen to have exactly the same methods to add and remove elements. So the designers of this hierarchy decided to move this up into the common superclass, which is collection. But now it's so high in the hierarchy that this code also applies to classes such as array, which are not extensible, and so they shouldn't inherit these methods. So in order to compensate for this deficiency, the designers then added some dummy methods in array that just override the methods inherited from collection and throw a runtime error. So whenever they are called, it's just a runtime error is thrown. They didn't do that for add all and remove all, because these methods actually depend on add and remove. And so they are now indirectly disabled as well. But of course, for the programmer, this is very hard to see. And it's now, as a consequence of this, very hard to understand what's the real interface, what's the real protocol of a class. So what's the real protocol of array? It's not immediately obvious. A case of inappropriate inheritance is, for example, the class dictionary, which inherits from set in order to share some code like size and union. But then other methods, again, the designers decided they don't make sense in a dictionary. And so they, again, added some dummy methods to say, you know, this shouldn't be inherited. We just throw a runtime error. But again, it makes it really hard to see what's the real interface of the class dictionary. And we may end up with unexpected runtime errors. Now, how do traits help to solve this problem? Our strategy to use traits in this hierarchy was kind of twofold. First, we said, in the first step, we create traits for the identified properties, for the identified criteria. So we have functional properties, so traits corresponding to functional properties, like extensible, explicitly ordered, and implicitly ordered. And we have implementation properties, like array-based or linked. And in a second step, we then said, OK, we combine such properties to create our collection classes. The resulting collection hierarchy then consists of 3 different layers. We have on top an abstract root class that now, in our case, only provides the facilities that are required by all collection classes. So only what's really supported by all collection classes is in class collection. Then we have a second layer of classes that correspond to common combinations of functional traits. And finally, we have a layer of concrete classes that correspond to the actual concrete collections. And they typically inherit from one of these abstract classes and then add some implementation traits or some other traits. For example, dictionary does now not inherit from set anymore. Instead, it inherits from extensible unsequenced, because it's an extensible unsequenced collection. And it then just adds the dictionary implementation trait and some glue methods, and that's how we end up with dictionary. Yeah, I mean,
it seems like most of these are single trait.
Right, so what we did is, I mean, there are lots of comments about this to make. So these classes only have a single trait, but this single trait actually is composed from many subtraits. So what we decided to make that, for example, here the trait T extensible sequenced explicitly, instead of having the class extensible sequenced explicitly using only that trait, we could have said this class uses a lot of traits, but we said, okay, we create the trait T extensible sequenced explicitly so that we make the behavior that we use in this class also available as a trait, so that maybe it's used somewhere else then.
What I was going to get at is, so I understand that you did that. Did you have to do any glue code to combine the T extensible TC code to T explicitly components into a T extensible sequence explicitly? Right.
Right, yeah, I mean, generally, I could look up.
There's a kind of an implicit assumption that these traits are orthogonal to one another, but they don't interact with one another, that extensible doesn't interact with sequence. So you can add one or you can add the other, and you don't have to implicitly do. The assumption is that you don't have to do the work to combine those two, right? And if you do have to do work to combine the two, then something has to be implemented in the class that's doing the.
Exactly. Right, so what we had to do in general, they were oftentimes pretty orthogonal, but sometimes you have certain things, how you need to connect them, or sometimes maybe a method that is kind of conflicting. And so in this case, we have some glue code actually, for example, implemented in T extensible sequenced explicitly. And that's where we put that glue code. Now, instead, we could have also said we do not want to have the trait T extensible sequence explicitly and just use all these other traits directly in the class extensible sequence explicitly and then put the glue code there. So it's just kind of a cosmetic thing that we that we did that.
So how would this compare if you had the Java facility of you could have multiple inheritance but only in interfaces, right? It would seem like the top part usually just is mostly interfaces, almost no methods implemented. The bottom part is single inheritance.
No, actually.
Remember, interfaces don't be so neither. I know, so the opposite remove all is not doable at a high level.
Right. No, what?
I'm just trying to understand.
Right.
What is up in the top part that's actually code as opposed to just
There is a lot of code. So actually, most code is in the upper part. So when I say this,
Actually, that's true. There should be something on there. How many methods are actually in all of these things?
Right.
Because if I remember this correctly, there's a lot of code up there, and there's very little.
Right.
Code
Yeah.
up here.
So most of the code is up there, and when I said these classes are abstract, they just miss.
No, that's the idea. I mean, this is basically what this is trying to do, is really provide you a wide range of behaviors based on very little requirements, and you fulfill the requirements and propose these things to make
Right.
more powerful things.
Right.
So one of the nice things is you can actually define the composition for an explicitly sequenced extensible collection already up there. You do not have to do this down here.
what are you going to define?
You would find methods like saying, okay, I implement add by extending myself by 1 and putting the thing in there.
Well, that's almost really wrong implementation, though. It's not really inefficient.
Well, it depends on what it is.
Most of the things I can think of.
Like a linked list, like the first thing that's down there. That
Might
seems
be okay
perfectly
for a linked
reasonable.
list.
As a matter of fact, this is, so here's the other thing. Extending by 1 may not physically mean resizing an array.
Might just be moving a limit.
Precisely. So that's the other thing. That's what we're saying. Okay, let's not worry about this implementation. And down here in the implementation, you would decide. For example, the linked list would extend by 1 by adding another object into a list. The ordered collection, what it does is putting up a limit until it hits the boundary, and if it hits the boundary, it resizes. So that's the code that you find down there, which is really the implementation-specific part.
Right.
But what you find up there is saying, okay, if you add something to an extensible collection, you get this. For me?
Yeah, the T extensible is going to do the logical add one.
Precisely. Yes.
Right, exactly. So that's also the separation. Here we mostly added, you can see this with the impulse, we added implementation traits. So we have here the logical behavior of an extensible sequence collection, and then whether you implement that with a linked list or an ordered collection, kind of more an array-based structure. This is really just a few methods. If you design it right, you have to change a few methods, and then that works.
If you look at the Dillon hierarchy, they would achieve a very similar result to this just by self-discipline. The language couldn't convey any constraints on whether it could say just by self-discipline and then manually coalescing the very simple and needed.
It's been noted many times that C++ could be used the same way that Java is used,
Right.
but nobody did.
Right.
That's what I meant. The one example that I saw which was a beautiful thing, which was basically consequently using abstract classes for interface inheritance and single inheritance for the implementation inheritance, which was wonderful.
For a lot of people, I think the initial exposure to Java, especially, well, for a lot of people, the initial exposure to Java's multiple inheritance with using interfaces is it's just a broken form of multiple inheritance. Not realizing until you program it for a year how powerful it is to think in terms of interfaces instead of in terms of multiple inheritance. Practically never use multiple inheritance, but
Right.
it's one of the nicest things about Java.
Right. Okay, also one thing that you can see here, we have the class set, and then one of the subclasses is an identity set, and there we could use the trait T identity adapter to kind of do that without implementing anything really in identity set, and the same trait T identity adapter we could then use to make a subclass of dictionary identity dictionary. So this is stuff you can also down here not really do with single inheritance, but still most of the code is implemented up there. So here it's just kind of the hooks, a few hooks remained open up there, and here they are just kind of filled in. So, okay. So what did we gain with that refactoring? On one hand, we gained consistent hierarchies. So there is no inappropriate inheritance anymore. We do not need to cancel any methods. So there are no methods implemented too high. Before, these were about 10% of the methods that really had to be disabled somewhere. And then the protocols are uniform and complete. So we always have complete protocols, and not just because we didn't want to duplicate code. We just implemented a few enumeration methods here and not the others. Then we also have less code. We refactored 38 classes with about 1,200 methods. And we created a total of 67 traits. And after the refactoring, we have about 10% less source code and about 20% fewer methods. Now, another advantage that is not so immediately obvious, but is really important, is that we also improved reusability. Because instead of having a few collection classes that have a lot of code in them, we have now a toolbox of quite small traits that can be used to create new collection classes, but also to create, to add collection behavior to other classes that are technically not part of the collection hierarchy. For example, there may be a class path which inherits from visual because it's displayable, but path is also a collection of point. So before, path does not inherit from collection because it has to inherit from visual, and so there is no collection behavior in there. But it's very useful to have collection behavior in this class path. And so how we can now do this, we can just say we add a trait, T enumeration, to the class path. We only need to specify what do means, and we get all the rest. So we can kind of have these groups of methods we can now plug in at other places and actually reuse them. Now in Java, we could say, okay, path now also implements the enumeration interface, but we had to do all the work ourselves. All these like 50 methods of the enumeration interface.
A variable containing a enumeration of points. That seems like a better idea anyways.
Because you wanna collect this thing into a path. When you do say like
right.
I want this path offset by 2 pixels.
Right.
You do not want a collection of points to get the path. You know what I'm saying?
No.
Yeah. But this is exactly the point.
Let's say let's call this let's say you want to create a path which is offset by 2 pixels to the right, right? What you can do is, you can get the point, collect the points, and then create a new path with these points.
Right.
In this case, what you could do is just, give me this path, collect the thing, and it will give you back a path instead of a collection of points. The path has more methods than just the collection of points.
Or if you wanted
There's a lot more stuff in there.
you could have collections.
Yeah, I'm thinking of type languages, and I'm not sure this actually works. But,
No, it's actually...
Actually, this might be hard to do in statically typed language.
No.
I don't know.
But I just talked to a guy who implemented this in a statically typed language with a type system very much like Java, and he said that he uses it a lot like that because he uses traits also as types. So he got rid of interfaces, said my interfaces are traits which can specify also some behavior. Right, yeah, I mean...
I think it's a programming methodology difference, though. Don't worry about
Right, no, I agree. I mean, there's a big question of whether you want to have interfaces and traits, or just he decided to, get rid of interfaces and just have traits. And so, yeah, anyway, of course you have to deal with the type issue, but if you wouldn't have that, if you would say, okay, we have interfaces and traits, then you just have to make sure that path now uses the trait T enumeration and the interface I enumeration, and you could actually deal with it. So it's not really a problem. Okay, now it's clear that some of these benefits that we achieved could also have been achieved with mixins and multiple inheritance. So we could also have used mixins or multiple inheritance to refactor our collection hierarchy. And so let's quickly compare these approaches. On one hand, it's clear that if we had done so, then the conceptual shortcomings that we identified earlier would actually have appeared in our hierarchy. We also compared our hierarchy to some implementations of the collection hierarchy with mixins, and that indeed is the case. Then even more important for us is that with these other technologies, you do not have the flattening property, which means that unlike with traits, there is a trade-off between fine granularity and understandability. As an illustration, the class order collection is now built from a total of 35 traits. But we just kind of said, okay, let's explore how detailed we can do that and how we built it like that. But nevertheless, with traits, we can still look and understand and work with the code where we see, okay, we have order collection, has a lot of methods, has some methods, extensible sequence explicitly has more methods, and collection. So we have 3 classes, and it's very much like it is implemented now. With Mixins, this would not be the case because order collection would actually inherit from 35 intermediate classes that may contain supercalls and whatever else. So it's actually important to know for these methods in what level they are. So you have to be aware of the whole hierarchy in order to really understand exactly what's going on. With multiple inheritance, it would look about like this. We had order collection inherit from 35 superclasses, one of which would be collection. And to really know what's going on, we had to consider that whole picture. That's why I said it's really important to have that flattening, because we could also expand this, of course, that it looks scary too, but you can actually also work with it that way.
I'm just curious, of the 35 traits that make up an ordered collection, how many of them are specific to ordered collection, and how many are used elsewhere?
Oh, that's a good one.
Yeah, I had to look it up. I have the, yeah.
Have a vague idea? Is it 10 to 20?
I mean, most of it is actually implemented up here, and so it's really reused. But it's more than a year ago or 2 years, so I don't know. But I have the implementation. And of course, it's clear that maybe 35 traits is a little bit too much, but we said, hey, if you don't have a trade-off, so let's make it really fine-grained groups of methods instead of individual methods. You know, we can always make bigger traits. And the nice thing is you can flatten at any level. If you're not interested in the detail, you just say, I don't want to see it. Okay, so in order to be able to do this case study and also other experiments, we did quite a few other case studies. We implemented traits in Greek, and the core of this implementation is a language extension that consists of 2 parts. We extended the language kernel to be able to represent traits, and then we modified the compilation process for classes built from traits so that they actually have the right behavior. What's notable is that we did not have to change the virtual machine for this, and I'm now going to quickly explain you why. We have here a class point that inherits from object, and in Smalltalk, each class has an associated method dictionary that contains all the methods of the class in forms of bindings from method selectors to method objects that are actually containing the actual bytecode. Now, if we send a certain message to an instance of the class point, what happens is that the virtual machine starts looking for the method in the dictionary that is associated to the class point. In this case, it cannot be found there, so it goes up the inheritance hierarchy and looks in the next dictionary. And here we can find the method hash, so it gets executed. Now, let's see what happens if traits come into play. We have here a trait tcolor, and like classes, also traits have an associated method dictionary. If we now use that trait in the class point, the compiler extends the method dictionary of the class with an entry for each of the methods in the dictionary of tcolor. However, it does not copy the actual method objects, because instead it references the actual method object. So the bytecode is not really duplicated. And this is possible because of 2 things, because of the flattening property, which says that the semantics is the same, and because there is no state in traits, so we don't have an index offset problem, so it just kind of works.
This is why you can't rename inputs?
Right, but again, yes, in this implementation you can't, but we have now an implementation where we combine that with the encapsulation mechanism, and there we have to do kind of name mangling and stuff.
You have to change the methods, right?
No, the way we do it, we actually have compile always with internal unique symbols, all the methods, and then we just have kind of we map them. It's a little bit of a different technique.
If one instantiation of tcolor red is mapped to orange and another one is mapped to blue,
right?
Don't you have to generate a different method code?
The way we do it in the other implementation is that we say we use internal symbols whenever we compile something, and then when a class uses a trait, we check if there is some renaming going on. We check whether we have to now map the internal symbols to.
You're talking about different things here. So the reason why you cannot rename input is that the names that you have in tcolor are part of the global selector namespace.
Right, that's what I asked before. You said they had a way around it.
Right, and what Nathanael said is the way around this is to say this is not part of the global selector namespace, but rather the thing down here has an own private namespace happens is you match this over into, you basically have a mapping
Right.
from this namespace down here to that namespace up there.
Right.
And when you have this mapping,
Yeah.
it's explicit, so you can rename.
Right. You have translation tables. I mean, it's quite a sophisticated implementation.
At runtime, when you run M5, you change the dictionary of selector lookups or something?
When you compile it, not when you run it.
Yeah, when you
Maybe
compile.
a different code for each instantiation of the trait.
No, it actually, you don't, no, you just extend, I can show you what we have then.
Blue code, I guess.
Yeah, to map it, we have additional entries in the method dictionary that refer to the same method. So one method can be referred to by two different names. So what we do is usually we use unique names, and then if two things mean the same, we refer them. So we do not have to change the method code because there are different ways.
It essentially adds blue code.
Right. But we do not have to actually duplicate bytecodes even with the implementation that actually works with the encapsulation. So the only exception to this is when a method contains a supersend, because in Smalltalk, methods that send to super, they contain a reference to the superclass in the literal frame of the method. And so because when we have a trait, the superclass is not known. A trait can be used to many different classes. So we cannot really fill that into the method, in this case, M7. So in this case, we actually really do duplicate. We copy the method over, and we put in the right superclass. So in this case, this would be object, so that everything works smoothly. Fortunately, this does not, this is a relatively small fraction of all the methods that contain supersend, so it's not too bad. So as a summary, we can say there is no modification of the VM necessary, so the lookup mechanism is the same. Then, nevertheless, there is essentially no runtime performance penalty. The only little, yes? Sure? Yeah? Right.
The implication there is that if you do, there is a forwarding pointer though in the class. So
Right. Exactly.
Yeah. So when Red wants to call angle, it actually calls 443267, which is implemented as a method they call angle.
Yeah. If Red wants to call angle,
It actually calls some internal symbol unique to that trait.
but what if Red is calling hue?
So
It's the same thing.
Red is calling hue. It calls it in the point class, or it calls it in.
No, it has to call the internal symbol because it could have been overridden, right? Which then has to call back.
Right.
To the trait.
But no, just
So it has to jump out. It's going to have to, yeah.
There's a lot of
Every binding
Right.
has to go back to that to this view table, the yellow view table, not the other.
Yes.
right.
Yes.
How,
Always.
note, however, in that implementation, in the basic implementation, without the encapsulation, there is no internal names. There is just everything uses the right names. In that implementation, if let's say red,
What if you rename red to orange?
Well, you can't do that in the current implementation.
What?
You can't do that.
No, not the input, the output.
right, then you just get, what you get is, yeah, you mean if you do an alias?
Yeah. What if you change the name of the method you're producing from the trait red to orange?
Right. Yeah. Okay.
There's now a new red method in the point class, right? They can't both be red.
Right. So.
Oh, wait, no, never mind.
Yeah. I mean, right. Yeah. Okay. I mean, we could go into lots of details here, but so anyway, the summary is that there is no modification necessary of the VM, and nevertheless, there is essentially no performance penalty because the only little price we pay is that we always use indirect instance variable accesses, of course, because
That's indirect method access too. Because that's not true.
no, actually,
The code is still there.
no.
No, well, remember, the current implementation doesn't do that.
Oh, okay.
Right.
The current implementation uses one global selector namespace. This is why you cannot rename these things on the input.
However, I mean, I can afterwards, I have a presentation for that too if you're interested. No, but I can go into details about the implementation with where we have the encapsulation mechanism. And even there, you can do all the work at compile time. We can do all the work there at compile time. So at runtime, you really only have the indirection through indirect instance variable accesses. And this is quite common practice in Smalltalk anyway for many accessors. And so it's not really, doesn't make a real difference for many cases. There is no duplication of source code. and there is only a small amount of bytecode duplication when we have supersense, then we actually duplicate bytecode. Okay, as a summary, we can say that I've shown that in certain ways, in many ways, traits are a better solution to some overuse problems than multiple inheritance and mixins. The reason for this is that they avoid many of the problems that I identified, and that traits also support the flattening property, which makes reasoning about traits, even if they are used extensively, quite simple. Then I've shown a case study that traits are also useful in practice. We applied traits to the Smalltalk collection hierarchy, for example. And then traits are quite easy to implement efficiently, thanks to two things. On one hand, the flattening property, and on the other hand, the absence of state. Last but not least, I would like to say that traits have had quite a significant practical impact since their invention. So the Perl community got quite interested in traits. So they are now ported to Perl 5, and I'm also got contacted by Larry Wall, the designer of traits, the designer of Perl and the main implementer, who says he wants to really use traits in Perl 6 as a standard feature, and so he's in the process of actually producing that now. Then traits have been ported to VisualWorks Smalltalk by Terry Raymond, who works for Syncom, the company making VisualWorks. Then Sun is working on a new language. This is Guy Steele, who also is one of the main guys behind Java. So he's now working on a new language, kind of an internal prototype as successor also of Java. And there is also traits are a built-in language feature. Then there is the language Scala. This is a typed language. It's a multi-paradigm language that has kind of functional aspects and object-oriented aspects. And their traits are a built-in language feature, which is particularly interesting because Scala has a type system very much like the latest version of the type system of Java with generics and everything. And this is fully integrated. And it's nice because we have only implemented traits in dynamically typed language. So this shows that it's also possible to use it in statically typed language. And they have a very big library where traits are used extensively. Then we are also collaborating with Microsoft on a research project to bring traits to the .NET platform. Currently, we are focusing the platform, but now we are wanting to pull it up into C#, not so much yet the other languages, but this is something that is still ongoing. More information can be found on my webpage. There you can, on one hand, find my thesis that contains all the work, but then also we have several publications on different conferences and journals that talk about several aspects of traits. Okay, thank you very much for your attention, and yeah, I'm open for questions.
And the problem was that people would step on each other's variables and violate assumptions about
Right.
how those variables were supposed to be treated violently. The difference between that, again, you are separating out code from data. So the part of the transition to object-oriented programming was treating units and encapsulating units, right? You
Right.
can't violate my assumptions anymore because you can't actually access the data.
Absolutely, yes. Right. Right.
Specifically integrates.
Right. Right.
So it's possible for people to step or to violate assumptions, but it's assumed that it's under the glue code's control that those assumptions are going to be controlled.
Right. Exactly. Right.
So you protect your semantics by using the glue class.
Right. So I mean, what in the first attempt also, when we really separate now the encapsulation issue from the composition issue, we really took that decision, which is a trade-off. It's clear that a trait is kind of a white box. If you use a trait in a class, it's kind of a white box form of reuse. So you use the trait in the class, and then the class is kind of responsible for not violating the assumptions the designer of the trait made. And if you override a method in a bad way, or if you do something wrong, then the thing breaks.
You can always break things, but I believe one of the good things about traits in this particular area is that it makes it actually possible to write tests for traits, which can then automatically be run on anyone who uses these traits.
Right.
And that, I believe, is a lot simpler in the presence of actually having some sort of code to look at compared to, for example, writing tests against Java interfaces, which I think is one of the hardest things to do.
The problem I see is, so let's take that path example where you made it also a what is it, enumerated sequence or whatever.
Yeah, enumerate. Yeah.
So what you're saying to me is that you have to go in and look at what the spec of the enumerated collection class said. You must have these 5 weird state variables that I don't want anyone except me to ever touch. And then you have to implement them, and then you have to promise not to touch them. And if the enumerator changes his state, you've got to go re-implement all that code.
That is
you
true.
failed encapsulation.
Right.
Yes.
No.
That is true. In this particular case, that is true. If you wish to encapsulate these things so that you cannot touch them from the outside, traits will not do that.
Alone.
They're not a silver bullet for
You don't care about the
encapsulation.
privacy, just the mutation issue. If I'm going to change my state of enumerated collections on a frequent basis, there's no way to reuse that trait.
I mean.
It depends, that also depends on the design that you choose. I think some of the things that were somewhat problematic in the examples here was that all of the requirements were always state, which I think is really
Right.
bad.
Yeah. This
it actually prescribes a certain implementation that is very hard to work around.
Yeah.
Versus what I would have expected is methods like acquire lock and release lock that actually said, I don't care what you do, but this is what I need.
Right.
This is what I need.
Also, for example, in most of the code that we actually wrote, when we refactored real hierarchies, then the requirements really weren't state. So for example, the enumeration is there is one requirement that's do. And you get about 50 methods if you say what do is. And the thing is that if you use that, of course, if you then you can have,
This is great for implementing collections. What if you want to use collections, like the path example?
Right, so when the path uses enumeration, the only thing the path needs to do, it needs to say, what is do in my case?
No, we have to provide state. An actual collection.
The path already has that.
If you want to use a collection, you use the class, you don't use the trait.
Right.
Right. And so class inheritance is still there. Or
Right.
class instantiation.
Yeah.
So you're saying
This is for building a class hierarchy.
So in
re-implemented a collection
let's
path.
let's take it as a concrete example. In path, what you would have is you would have an instance variable points, which is a collection. And the path itself would implement the enumerable trait to say, I wish to provide these methods, just as native methods of path, basically.
Imagine in a statically typed language that you were that like C++, that you wanted to avoid the use of templates. Traits would make a wonderful way of doing statically typed trees without having to
Right.
the same kind of template.
Well, assuming you have types in as well as methods.
What's that?
You don't build a path type to those, you do that.
You have to be on the dynamic path.
Right.
No, I'm a set type, so.
Oh, I see.
But
Sometimes it's much harder.
no, but actually, but in fact, I mean, this is one of the reasons why Microsoft is interested in that, and also Sun. What is it? Like C++ templates you can use for 2 reasons. On one hand, you can have generic. So you can make a generic container data structure that can deal with a lot of different types of elements. But at the same time, templates can also be used to kind of, in a way, like mixins. And by restricting, like in both C# or like the .NET platform and Java generics, you cannot use this kind of, you cannot, for example, have a parameterized superclass. In C++ templates, you can have a parameterized superclass, and so you can do a lot of like mixin-like things. You cannot do that. And so they think, the problem is you could do too much. And so this was too complex.
If I want a list of ints out of traits, then I've got to be able to pass int as a type
Right.
into the trait. So in addition to, if it's applied and required, you have to have types as well as methods. And then you get fun recursive types. And it gets interesting.
No, but that's completely in Scala, also in our .NET specification. That just works with the generics mechanism of .NET or Java. You can say a class can be a generic class, and it can expect some type parameters. And in the same way, a trait can be a generic trait. And that's what I say. In the same way, you just make the same generalization in the same way as a class can be a generic class, also a trait can be a generic trait. So if you use a trait, you say, I use a trait, and the type parameter t is an int. And that's that. I mean, it's working.
Better now. I'm suspicious, but
Yeah, okay. I can just tell you that, yeah, that it's working and it's used by, people who design Java. Like, yeah.
Well, we've seen how well that works.
Yeah, okay, I agree, but I mean, there are people who design Java or know that Java is, or like at least they're maintaining Java. Maybe they know about the problems in Java. So, yeah. And also, yeah, I mean, I know people who do, Yeah. Yeah, okay, you're welcome.